So let's start by looking at how the tropics and the diabatic heating in the tropics can force the extratropics, and then we'll see how the extratropics gets back to the tropics. Here we are with the Madden-Julian oscillation figure that we saw before. So we will see more specific examples of this in the broader schematic that we had seen, where we said tropical heating can set off these wave patterns like the Pacific North American pattern. There is a similar Pacific South American pattern that's not shown here. And there is, of course, the low frequency climate modes like the El Nino Southern Oscillation, Indian Ocean Dipole. There is the Wörtke jet, monsoons, South Asian, East Asian monsoons, winter storms, wildfires, cyclones, winter storms up here, tornadoes even included, hurricanes, of course, cyclones and hurricanes, droughts, heat waves, NAO, we had mentioned, Arctic oscillation, Antarctic oscillation, Antarctic circumpolar current, and so on. And the idea was that if there is predictability in the MJO, it can be predicted 3-4 weeks ahead, then using these relations at subseasonal timescales, there is potential predictability of these specific events like wildfires and cyclones and cyclogenesis and hurricanes and monsoon intraseasonal variabilities, which we will visit. To look at specific examples of these things, let's go through a few. This is showing here 850 hectopascal wind for November to April, and it's the same for months for 200 hectopascal winds, so low level and upper level winds, and you can see the features there very clearly. This is showing composites of wind anomalies at 850 and 200 hectopascal for days when the second principal component of the 30 to 60 day bandpass filtered 250 hectopascal velocity potential daily anomalies exceeds 0.85 standard deviation. So it shows a certain strength of activity, indicating convection in the western Pacific Ocean. OLR composites composite anomalies of 5 watts per meter squared are superimposed in the dashed contours, and the main story is, of course, that there are certain longitudinal locations where tropical heating is very efficient in forcing the extratropics, and there are certain longitudes where the extratropics are able to reach into the tropics. Turns out in the East Pacific and the Atlantic Ocean, where there is upper level westerlies, which you cannot very clearly see here. So the westerly duct and the so-called tropical upper tropospheric trough allow extratropical signals to come back. But this particular figure is basically trying to argue that when there is strong convective activity in the Indian Eastern Pacific region, you can see associated signatures you can think of as wave trains here, low high kind of bands, both at the lower level and at the upper level. Okay, so there is a entire atmospheric forcing in the extratropics, mid-latitudes all the way to very high latitudes by very strong tropical convective activities. Similar figure here done with lagged composites of northern hemisphere 500 hectopascal geopotential height with respect to MJO phase 3. So again, that corresponds to a certain location of the heat source convective phase of the Madden-Julian oscillation in the longitudinal position. Remember, 1, 2 are in the Indian Ocean, 3 is over the maritime continent again. Contour interval, so this is done as a lag of 5 days, 10 days and 15 days, and I won't go into the details, but the orangish colors are where the signals are statistically significant at 95% confidence, and the red and blue colors correspond to geopotential height anomalies with respect to the background. So these are subseasonal signals, obviously pentads 1, 2, 3. And the main point again is that the same things that we saw here are seen clearly as 500 hectopascal geopotential anomalies, which, as you know probably, in the mid-latitudes correspond to weather anomalies and are good quantity to predict, to get some extended range predictions out of those. Another example here, lagged composites of 2-meter air temperature anomaly in the North America with respect to MJO phase 3. Again, you can see that pentads 1, 2, 3 are shown. Okay, lag 0, so 0, 1, 2, 3. And the point again is many statistically significant signals of positive and negative 2-meter temperature anomalies, which obviously, especially in the winter season, can indicate related processes like snow, thunderstorms, and other things, especially when you have the warm Gulf of Mexico sitting here, which can always pump lots of moisture to meet the colder air coming from the north to create the thunderstorms that much of US is known for, as well as Tornado Alley in this region, which we saw that MJO has an impact on tornadoes as well, right? So the intraseasonal variability in the tropics also sends signals into the subtropics of the Indian subcontinent and East Asian monsoon regions. We had seen this before, where we are looking at the climatological daily rainfall with deviations from it for 72, 94, and 2002, El Nino year, El Nino year, and El Nino year. And you can see, normal year and El Nino year. So you can see that changes in the active break period characteristics based on whether it's a normal year or a dry year corresponding to an El Nino. The modulation of synoptic scale variability by these tropical intraseasonal oscillations propagating northward also happens as low pressure systems or monsoon depressions. So you can see genesis and northwestward propagation of these systems much more during the active phase, so these blue periods here, than during the break period. Okay, so these bring up to 60% of the rainfall over the core monsoon zone, for example. So this is another good example of how tropical diabatic heating propagates energy into the subtropics and modifies the monsoon variability at critical time scales of active break period, which are very important for the crop calendar. So the entire agricultural system during the Kharif season over India depends on these active break periods, and any predictability at those time scales are very critical for managing the crops, irrigation, ensuring there is no crop stress because of soil moisture, crop damages, and so on and so forth. Even the sowing after onset is based on these extended range forecasts. So obviously tropical heating drives subtropical, extratropical circulation anomalies through either waves or the eddy fluxes. It turns out that waves are a smaller part than the eddy fluxes, which we will look at in a little bit more detail. And the location of the heating matters because the links between tropics and extratropics and back depend on things like the stretching. So waves propagating around in the background flow are affected by gradients of the background flow, du dx kind of term, where x is the zonal direction, u is the zonal velocity, or also du dy, where the meridional gradient of zonal winds can also matter for how far the equatorial heating signal, as Rossby waves, for example, can propagate into the extratropics. Okay, so we are kind of going a little fast in terms of the processes, but as I said, all those processes are discussed in detail in the tropical dynamics course that I have on my channel that you can look up if you are interested in getting into more details. Okay.